Before watching this playlist, please watch my playlist for Hopfield networks because you will see how Boltzmann machine can be seen as generalization of Hopfield networks. In this playlist, I will talk about different kinds of Boltzmann machines, such as general Boltzmann machine, restricted Boltzmann machine, and many other types of Boltzmann machine. But restricted Boltzmann machines are invented by Geoffrey Hinton many years ago, and it's very important. And for example, deep belief networks uses these ideas to generalize and make it deeper. Because, for example, restrictive Boltzmann machine is just one of these, and so we try to I try to explain different kinds of Boltzmann machines that are inspired from physics and sometimes biology. So there are two great, amazing scholars. For example, Geoffrey Hinton and Ali Ghodsi. They teach these things on YouTube very well. And what is the history of Boltzmann machine? Boltzmann machine is based on spin glass model. And the original contribution is applying such energy-based models in cognitive science. And the seminal publication of John Hopfield that I explained in my playlist for Hopfield networks connected physics and statistical mechanics. The idea of applying the Ising model with Anneal Gibbs sampling and similar ideas. So Ising model became considered to be a special case of Markov random fields, which find widespread in linguistics, robotics. So there are different types of Boltzmann machine. Some of those neurons are hidden units, and some of them are visible units. Just like hidden Markov models, conditional Markov models, and many other graphical models. So when we say restricted Boltzmann machine, it means that there is no edge between the observant nodes or even hidden nodes. There is no edge between them. When we say deep Boltzmann machine, we want to generalize it, stack it, and having a deep layers. But I think this one is more related to our human brain. Of course, this one has been seen in the relation between neocortex, if I consider it for your unconscious mind, long-term memory, and your hippocampus. Hippocampus I've written 3 articles on my Medium account about hippocampus and its relation to artificial intelligence. So hippocampus is connected to neocortex, just like a restricted Boltzmann machine that we have hidden units and we have observed units. So they are connected to each other. This is the article that I was explaining. It is using these restricted Boltzmann machine that I will explain for hippocampal models. So somebody asked Yoshio Bengio prefers restricted Boltzmann machine or autoencoders, denoising autoencoders. And he said, we are interested in understanding, and of course autoencoders are somewhat easier to train, but it is better, as he said, it is better to understand all of models that for unsupervised learning, such as Boltzmann machine, autoencoders, denoising autoencoders, variational autoencoders. There are many paradigms in machine learning for unsupervised learning. And if we learn all of these models, then we can see pros and cons of each of the models. And gradually, eventually, we develop models that have more pros than cons. So, what is restricted Boltzmann machine? As I said, there is no edge between the visible nodes, so there is no edge between these nodes, and there is no edges between the hidden neurons. They are just connected by these weights. So we want to design weights. Of course, not only we want to design weights, but also we need to define these biases as well. So all of these W, C, and B, let's call them theta, the parameters, because at the end of the day, for machine learning experts, you need to maximize your likelihood. And of course, here we are using unsupervised learning because we are giving it just a bunch of data. There is no label here. Everything is just your visible data, your data. There is no label. And the partition function is intractable, just like many problems in graphical models and machine learning. So the trick is used, for example, I love MCMC, Monte Carlo Markov chains. You go from that, you ignore the denominator, you see it's enough to say it is proportional, and after a while it converges to the stationary distribution. So you can watch my playlist for Markov chain that I explain all of those things and what is the properties and all of those things about Markov chain. Because you need it for Markov chain, Monte Carlo, MCMC. And so the distribution, this is the energy function. Now you understand why you need to see my playlist for Hopfield networks, because I used energy function. And here we use energy function, but a more general energy function that not only we have some weights, but also we have some biases C and B. And H is your hidden states here. V is your observation, your data, for example, your MNIST data, or recommendation movies or anything. But most of the time when we talk about restricted Boltzmann machine, we are working with binary states. For example, 1, 0, 1, 0, 1, 1. And 90% of articles, they are working on binary data. And so this is a beautiful slide from Geoffrey Hinton that Z is not tractable, so we use MCMC. So the probability of your hidden state, given your value, your observation is this. But Z is intractable. And if you solve this, if you go through that, you will see it's just a multiplication of these terms. And then normalize it with a different kinds of normalization that Ali Qudsi is defined in his lecture. So this is a distribution. We can compute this easily if we just condition on something. And we use Gibbs sampling. We sample from this. It's a very tricky, all of these restricted Boltzmann machine, especially in this playlist, in this lecture, because you will see that they simplify many expectations and those things. But it works. But I don't think biological systems do this. They use this complicated way of training. So that's why we are missing something that we should discover. So we sample H from this probability. We can simultaneously and independently sample from all elements given your observation. So now we have H. Now we have sampled that. So conditioned on that sample, we sample your observation. So first we have the condition on your observation. So let's say these are V nodes, these are H nodes. So we condition on V, we assume that we know V. We sample H, we know H. And then we assume that we know H. Condition on that, what is the probability that V is something else? We sample V. And at the end of the day, you need the log likelihood. You might maximize that. So these are parameters that I said. These are, let me call it theta. And because those are the parameters that you should learn by your training. And so this is theta, as I said. So the likelihood is with respect to theta. And if you take the gradient, because you need gradient descent, anything, to update the parameters. And so when we go through this, you have two terms: gradient of minus energy and gradients of minus energy of. So these terms this is about your model. It doesn't say anything about your samples. On the other hand, these terms tell a lot about your observations. We have different observations. We have n observations. So we go through that. You see the derivative with respect to W is HV. The derivative with respect to B is V. The derivative with respect to the gradient with respect to C is H. This term becomes 0, 0, so it remains H. And if you go through that, you can calculate, but it is impractical to compute the exact likelihood gradient. So that's why we use contrastive divergence. Instead of expectation, we say expectation of something, we say something, just evaluate it. That is a trick that is not scientific, is not mathematical, but we use it because it works. In machine learning, we do many things that are not scientific, but it works. Because we are doing something like stochastic gradient descent and those things that eventually solves our problem. It's like a magic. But biology is not magical. For example, Hebbian rule, what a beautiful rule. And you update, for example, the two neurons, the delta omega ij between neuron I and j by just multiplying, for example, kisi I and kisi j. So it's very natural, these things. But in machine learning, we do many things that are not natural. And that's why we have problems. For example, we invent something like contrastive divergence because we don't know what to do, how to handle these things. Maybe we are too involved in mathematics instead of understanding biology. I don't know. So this is the pseudocode. For each training example, we generate a negative sample using k steps of Gibbs sampling, and then we update the parameters. These are parameters, theta that I mentioned, that because we know the gradient, we just substitute this. And of course, we are using negative samples using Gibbs sampling. The two examples for the application of restrictive Boltzmann machine are, for example, this Recommender movie. For example, the Matrix movie, I like it very much. And this is the only movie I like. among Harry Potter, Fight Club. Fight Club is also interesting because I like psychology. So the matrix, for example, is related to, for example, it depends on the rate of movies, and also we have latent factors such as drama, fantasy, action. For example, if 1, it means it is action. If 0, it means it is not fantasy. If 0, it means it is not drama. And so you relate those things with it. So you can see it as a generative model. For example, you want to see, give me a set of movies that are like it is drama, but it is not fantasy, a little bit action. So it generates a set of movies. So or generating digits. You have 3. It generates many digits, such as this one. It samples for you. So there are pros and cons of restricted Boltzmann machine. The advantage is that the hidden layers can be included in other models as valuable features to boost performance. Due to limitations and connections between nodes is faster than a standard Boltzmann machine, efficiently computed and expressive enough to encode any distribution. But what are the cons? The cons are the backpropagation is more well known, and historically it is much easier to use than these things. And secondly, because it is challenging to calculate energy gradient function, training is more challenging. As you saw, we use lots of tricks, contrastive divergence, and those things that biology doesn't believe it. And weight modification, this is a disadvantage.